Alright, welcome back everybody. This is our second video on section 9.2 of AP Calculus BC, second derivatives of parametric equations. In the last video, we introduced the method for finding d squared y dx squared when given a parametric curve. And in this video, we're going to continue finding that second derivative, d squared y dx squared, given a parametric curve. And we're also going to use that parametric curve to answer some questions in these examples. So let's start here with example 2. We're going to find the concavity of the graph defined parametrically by x equals t squared minus 4t and y equals t to the fourth plus 2t minus 3 at t equals 3. Okay. So we're going to start, in order to find concavity, you should remember from earlier in the course that the concavity of a curve is based off of its second derivative. When the second derivative is positive, the curve's going to be concave up, and when the second derivative is negative, the curve's going to be concave down. So we're going to go ahead and find the second derivative. So I find dx dt is equal to 2t minus 4, and dy dt is equal to 4t to the third plus 2. Therefore, dy dx is equal to 4t to the third plus 2 all over 2t minus 4. Now I'm going to go ahead and find the derivative of that with respect to t. And we're going to need to use the quotient rule. So we've got low times the derivative of high minus high times the derivative of low. We'll square the bottom. And then I'm going to go ahead and simplify this. Let's see, that's equal to 24t cubed minus 48t squared minus 8t cubed minus 4 and combining our like terms, did I multiply all that out correctly? Yep. And so this is going to be equal to 16t to the third minus 48t squared minus 4 all over 2t minus 4, the quantity squared. And so the second derivative, d squared y dx squared, is going to be equal to this divided by dx dt, so divided by 2t minus 4, which when I take this fraction and I divide it by 2t minus 4, it just makes my denominator 2t minus 4 to the third power. All right, now we want to find the concavity of this curve at t equals 3. So we're going to go ahead and evaluate this at t equals 3. So that's 16 times 27 minus 48 times 9 minus 4 all over 2 cubed. So let's see, 16 times 27, that's 432. 48 times 9, also 432. Seriously? Yeah, that makes perfect sense. And we end up with this value being negative 1/2 at t equals 3. Therefore, since the second derivative is negative, this is going to be concave down at that point. All right, let's go ahead and we'll move on to example 3. All right, in example 3, let's see, consider the parametric equations x of t equals t squared plus t and y of t equals t cubed minus 2t. Find the intervals of t for which the graph of the parametric equation is concave up and concave down. All right, I'm going to scroll down a little bit here so that I can reach this a little bit more easily. So first I'm going to go ahead and find dx dt. Dx dt is going to be equal to 2t plus 1. And I'll find dy dt. Dy dt is going to be equal to 3t squared minus 2. And so dy dx is equal to 3t squared minus 2 all over 2t plus 1. And then I'm going to go ahead and take the derivative of that with respect to t. That's going to be low times the derivative of high minus high times the derivative of low, square the bottom, and away we go. All right, so let's go ahead and simplify the numerator of this expression. And we've got 12t squared plus 6t minus 6t squared plus 4 all over 2t plus 1, the quantity squared. So this is 6t squared plus 6t minus 4 all over 2t plus 1, the quantity squared. Oop, that's plus 4. All right. And let's see, if I find my second derivative, d squared y dx squared, I'm going to take the derivative of dy dx and divide it by dx dt. That's just going to turn this into 6t squared plus 6t plus 4 all over 2t plus 1, the quantity cubed. All right. And now I need to see what's going on with the concavity of this curve. Now let's see, 6t squared plus 6t plus 4. Let's see, b squared, that's 36, minus 4ac. So my discriminant is negative 60. So this has no zeros, which means my numerator is always positive. Numerator is always positive. So the denominator is going to determine the concavity. 2t plus 1 is greater than 0 for t greater than negative 1/2. And 2t plus 1 is less than 0 for t less than negative 1/2. And therefore, when the denominator is positive, the numerator is also positive. Positive divided by a positive makes it positive. Therefore, our graph is concave up on the interval from negative 1/2 to infinity. And it is concave down. Again, the denominator is negative for t less than negative 1/2, and the numerator is positive. Positive divided by negative gives me a negative, so it's going to be concave down on that time interval. All right, and there we go. A few examples using the second derivative of a parametric equation. All right, everybody, that's it for this video and it for this lesson. Come back next time for section 9.3, finding arc lengths of curves given by parametric equations. All right, and we'll see you then. Have a great rest of your day. Bye-bye now.